So it's 12 o'clock. So let's start our talks of our session of this afternoon. So the first talk will be of Professor Xiaoyang Chen. He comes from Tongji University, and he will talk about a Sharpie estimate on the size of the fiber of certain local biholomorphisms.
Thanks for the invitation. It's my pleasure to give a talk here. Okay, so today I'm going to talk about a sharp estimate on the size of the fiber of certain local biholomorphisms. So let's start from, well, okay. So let's start from the background. Of course, our motivation comes from this famous conjecture called Jacobian conjecture. This conjecture, of course, everyone knows it's famous, says every polynomial local biholomorphism is injective. If it's injective, actually it must be bijective. Well, this conjecture, of course, is very difficult, and so far it's still open. One can also study a general problem, right? So you look at the local diffeomorphism between smooth manifold. So you ask when it's bijective, right? So this is a generalization of this conjecture, and in this direction, there is a classical result. Actually, this result is very useful in Riemannian geometry. So this result is so-called Hadamard-Plastock theorem. There are many versions of this theorem, but I just stated in this form. It was useful in Riemannian geometry. So the theorem tells us if F is a local diffeomorphism between two smooth manifolds. So let's say these two smooth Riemannian manifolds are complete. Actually, we just need X1, T1 is complete. So F also satisfies this inequality. So if look at the V, it's a tangent vector on X1. Then you look at the differential F and V, the norm of this guy. Of course, the norm is taken with respect to G2, and it's big or equal to the norm of V itself. This norm is taken with respect to the metric G1. Then the conclusion is F must be a covenant map. So in particular, if X2, if X2 is simply connected, then it must be bijective, right? So this is actually a very useful result in the proof of the famous Hadamard theorem in Riemannian geometry. It says if you have Riemannian metric with non-positive sectional curvature, if the metric is complete, then the universal cover of this manifold is diffeomorphic to Rn, right? So in particular, the differential map must be diffeomorphism. The proof actually using this fact, because you look at differential map then satisfy this inequality. So then apply this theorem, you get the differential map with the covenant map. If you look at the universal cover, then must be a diffeomorphism. So I think Hadamard and Plastock, they proved this theorem for X1 and X2 is Rn, and then it was generalized to Banach space. But later on, people discovered it actually works for any Riemannian manifolds. So it's really a useful fact in Riemannian geometry. The proof actually, right, using some arguments from covenant space. So it's topological argument, topological and geometric argument. So of course, this theorem itself is useful, but of course, it cannot be used to prove Jacobi conjecture. Right? That conjecture is still very difficult. So, but this is also useful. So this means you can, instead of looking at this conjecture itself, it's too difficult. People try to study a general problem and try to find some conditions. Then it's hopeful to prove such local diffeomorphism is bijective. Okay, so in the spirit of this idea, so in recent years, actually, some new topological and geometric ideas have been introduced in the subject of global injectivity, so pushing the field in different directions. So the idea is the global injectivity actually sometimes is influenced by some more subtle topological phenomena. So we just mentioned some of this work. So most of this work, as far as I know, they are initiated from the work of friend Xavier. Yeah, from Xavier. So the first thing I mentioned is actually this Tabrian Baharia. Actually, I think he's a student of friend Xavier. So this theorem tells if you have a local diffeomorphism, F for Rn to Rn, it's injective if and only if the pre-image of every alpha hyperplane is non-empty and acyclic. Acyclic means if you look at the pre-image of this hyperplane, the homology must be 0 in every degree. The reduced homology is 0 in every degree. That means it's homotopic to a point. So this is a geometric assumption, right? This is a geometric assumption. So under this geometric assumption, then the conclusion is this map is injective. If it's local diffeomorphism, then it's global injective. This works for local diffeomorphism. Then another thing I would like to mention is this is joint work with this is joint work Leonard and friend Xavier. They said of course they prove a much more general version, but the simpler case they prove is if you start a local biholomorphism, it's biholomorphism. It's from Cn to Cn. It's injective if and only if the pre-image of every complex line is non-empty and simply connected. So let's compare these two theorems. The first theorem is F is local diffeomorphism, right? Then the second theorem is F is local biholomorphism. So they all look at the pre-image of some subspace, right, in Cn or Rn. The first one is they look at the hyperplane, the pre-image hyperplane. Then the assumption is this is acyclic. So it means the higher every homology group is 0. So this guy, they look at the pre-image of a complex line. So then assume this is simply connected. So this is a geometric assumption, then the conclusion is injective. It's quite interesting, the second theorem, because if you take F is a polynomial biholomorphism, if you take the polynomial biholomorphism, so you know by elementary algebraic geometry, you can show for every generic complex line, the pullback, the pre-image is simply connected. Yeah. So, but of course, this theorem, we have to assume for every complex line, the pre-image is simply connected. Otherwise, you apply this theorem, you can prove the Jacobi conjecture, because this conjecture says if you have a polynomial by local biholomorphism. So it's hard because this is algebraic condition, right? This is algebraic condition, but it's hard to check whether this algebraic condition implies the geometric condition or not, right? We don't know. We don't know how to show that algebraic condition implies this geometric condition or not. So just we look at some other conditions instead of the algebraic condition. We look at some other geometric conditions. Then you want to prove the same conclusion. So of course, the proof of these two theorems, they are purely topological and geometric ideas. Of course, if you study the famous Jacobi conjunction, you can use algebraic geometry, right, or algebra, because the condition is algebraic. But we change to a different direction. So we put algebraic, geometric and topological conditions. Then you apply tools from Riemannian geometry and topology, try to prove this injectivity of local diffeomorphisms. So let's say something about the proof of the second one because it's useful in our work with Frederico Xavier. So, for example, if you try to prove the second one, you argue by contradiction. So it's enough to prove the preimage of 0 is just 1, right? So because you move the point to 0. So if the preimage of 0 contains at least 2 points, P1, P2, then you look at any complex lines passing through 0. So 0 is a point in the image. Then you look at the preimage of this complex line. The preimage of this complex line is a manifold, right? Because F is a local biholomorphism. So in particular, it's transversal to the complex line. So by transversity theorem in different topology, you know the preimage of this complex line is a 2-dimensional manifold. It's 2-dimensional manifold, so it must be Riemann surface. And the Cn, there is a canonical metric. This metric is flat, right? So this preimage of this complex is a complex submanifold of the Cn. Then using the induced Riemann metric, it's a Kähler metric. It's Kähler metric, and the curvature, the sectional curvature actually is non-positive because it's a 2-dimensional manifold, right? So the sectional curvature is non-positive, and by assumption, we assume it's simply connected. Right? We assume it's simply connected. So it's got an Adamant manifold. It's got an Adamant manifold. That means for any P1 and for the 2 points P1 and P2, there is a unique geodesic connecting P1 and P2. So there's a unique geodesic. Then you define a section from CPn-1 to the canonical line bundle over CPn-1, because CPn-1 is the equivalent class of every complex line through 0, right? So you set L is complex line. L is complex line is the point the complex projective space. So you define SL equals to df gamma prime 0. Well, gamma is a geodesic, right? So gamma prime 0 is non-zero because P1 is not P2, it's not equal to P2. So gamma is a non-constant geodesic. Well, because F is local biholomorphism, the differential of F is isomorphism. So that means SL is not 0 for any L. So now we have constructed a no-well vanished section of the canonical line bundle L over CPn-1, right? But this is impossible because this line bond has non-trivial, has non-zero Euler class. They cannot be such no-well vanished section. So then you get a contradiction. So the argument actually is quite simple, right? But the proof actually using Riemann geometry. So you apply geometric and topological tools to understand the injectivity of these maps. So this is a simple model actually. Under this idea, using these ideas, they have actually proved a much deeper theorem. And there are several other works I don't want to mention here. They try to apply surgery theory and more complicated topological tools, and try to prove the same kind of theorems under different topological and or geometric conditions. So here I just mentioned a simple example. Okay, anyway, so Leonard and Frederico Xavier, they push these ideas very deep. So try to using geometric and topological tools to understand the injectivity. Also, they also apply tools from partial differential equations. So this is some kind of another direction. Okay, so now what I'm going to say next is the following problem. So instead of find conditions ensuring that a local diffeomorphism between smooth manifold is injective, we can also try to estimate on the size of the fiber of local diffeomorphism. So that means we maybe have a local diffeomorphism which is not injective. We want to ask, what is the size of the preimage of a point, right? it could not be injective, but what's the size of the fiber? So this is a question. Now the cell I proved with Fred Xavier is the following. We found such a thing. So it's such a. So here also we assume X is a non-compact complex manifold of dimension at least 2. So in particular, if you take X is Cn, right? So F is a local biholomorphism, and you take Q at any point in the image of F. So now we assume X carries a complete Kähler matrix of negative holomorphic section. So in particular, if you take X is Cn, then the yes, if you take it as Cn, such matrix also exists, but the matrix is not a standard matrix. It's complicated. It's not a standard matrix, but such matrix exists. And also we assume the pre-image. If you take a generic complex line, of course, for generic, we have to define what is generic, right? But that means usually means if after some, if you take away some exception means usually means invariant or some hypersurface. So if you anyway we call it generic. If you take the generic complex line through Q, if you look at a pre-image, if it's simply connected. The third condition is we assume if you have some other exceptional complex line through Q, if you look at the pre-image, the pre-image of this complex line has found many complements, Each complement may be not simplicated. We don't require this. Then under these assumptions, we can prove the following. Then the fiber, the pre-image of this guy is finite. Actually, we can have the following estimate. The estimate is the following. The pre-image of this fiber is less or equal to this guy's. It's if you first take the minimum and then the maximum. So the interesting thing is we look at this exception line. By assumption, we assume this exception line has finite many complements, right? Then we look at the number of connected complements of these guys. Then this guy is upper bound of the pre-image of this guy. Well, this theorem actually at the first glance is look very complicated, right? But we just compare with this theorem. So it's a generalization of this theorem actually. Say this theorem it works for Fx is Cn, right? But Cn carries a matrix with a negative holomorphic section coverage. Now in this theorem, actually there's no exception line, right? We assume every complex line is simply connected. But now in this theorem, we just assume the generic complex line, the pre-image of this line is simply connected, right? So, and we have some, we allow some exception lines. If you look at the pre-image, then had finite many components. So in particular, in this theorem, there's no exception line. There's no exception line. So then that means the right-hand side actually is 1, right? Because for any complex line, the pre-image is simply connected. In particular, is connected. So just has 1 component. So the number of this guy is 1. That means the fiber has exactly 1 element. So F must be injective, right? So this is a generalization of this theorem. We do not assume it's simply connected for every complex line. So as a conclusion, we cannot prove F is injective. Actually, their example will let me show cannot be injective, actually. It's not injective in general. So we want to ask how big is the fiber, right? How big is the fiber? We can find the estimate of this fiber. Okay, so let's say some examples. So actually, it's very essential that the pre-image of each exception line has only finite many components. Otherwise, the fiber may be infinite. So, or the simplest example is the following. If you look at a local biholomorphism F from C2 to C2, so this is a local biholomorphism, right? Yes. So if you look at the preimage of 0, 0, then the number of this preimage actually is infinite, right? Because if you take Z2 is 0, then you take e power Z1 minus 1 is 0. So, but this is a periodic function, right? So you have infinite many points per image. So actually the preimage of 0, 0 actually is infinite. However, if you look at the preimage of the complex line, what is the complex line over 0? There are two different kinds of lines, right? The first one is omega 2 is equal to lambda omega 1, right? So you can check the preimage of this guy is a graph. So it's simply connected. I call this guy's a generic complex line. There is an exception line. The exception is omega 1 is 0. If you set omega 1 is 0, then that means Z2 is 0, right? Z2, no, I'm sorry. That means e power 0, 1 minus 1 is 0. So that means the preimage of omega 1 is 0 is the union of these guys. Is the union of these guys. Well, there are infinite many unions, right? There are infinite many components. Well, each one is simply connected. So for the exception line, the preimage does not have finite many components. So the preimage actually is not finite. There are infinite many points because this guy, right? So that means we assume the preimage of every exception line has finite many components. This is important. If it's infinite, then the number of the preimage may be infinite. The second example we are going to talk about is the estimate actually is sharp. So the estimate is sharp. So that means the equality can be obtained. In the estimate, we get an inequality, right? So actually the inequality can be obtained. The estimate is sharp. So we also look at example F. We look at examples. So let's start from some simple function. This function is the product of this linear functions stuff. These linear functions. Now we want, of course, this function is not a local biholomorphism, right? Because it's not a local biholomorphism. So, but we want to show we want to construct local biholomorphism. So let's do some tricky part. So we construct an entire function phi, and you want to construct this guy's function f. So then we construct a function f. So this is quite a technique, but the important thing is after you do this tricky construction, we have a function f. The f prime 0, not 0 everywhere. So you do this construction stuff, we have a function f. So f actually is a map, right? It's a map. It's function. I'm sorry, it's function. So f prime is not 0. So then you construct a map. Here's the map I'm going to construct. It's again a map from C2 to C2. So this is f Z1 Z2. Because f prime z is not 0, so the Jacobi determinant of f actually is not 0. That means the big F is a local biholomorphism. The big F is local biholomorphism. So now you look at the preimage of 0, 0, right? So then you set Z2 to 0. So FZ1 is 0. So FZ1 is 0. FZ1 is 0. But this guy is not 0, so must have PZ is 0, right? So what is PZ? PZ is this guys. So if PZ is 0, then Z must be equal to J, right? J from J is 0 and K. So the fiber of 0, 0 has precisely K points. Yeah, has a precisely k points. So then if you look at also the preimage of the complex lines, right? Again, the generic line is this guy, omega 2 is lambda omega 1. So it's again, it's simply connected. Now we look at the exception line. Exception line is omega 1 is 0. Omega 1 is 0. So then you look at the preimage, right? Omega 1 is 0, so you have FZ1 is 0, right? FZ1 is 0, so you have this guy. So just is F prime. So yes, F. So this the preimage of this exceptional is a union of these guys. So which has precisely k connecting components. And so this is the same number of the points in the fiber. So that means in this particular example, the equality in the CM is obtained. So that means that our estimate actually is sharp. Okay, so this actually is very nice example. So there's another one I want to also tell you is in the third in the CM, the topological hypothesis that the preimage of the generic lines is simply connected is essential. Yeah, we have to assume the preimage of generic lines is simply connected. Well, if it's not true, then the conclusion is again false. So let's start from these examples. So we know every metric on a real orientable real surface is killer, right? So relative to the complex structure. So we can look at the C minus point, C minus this point. But this point, this Riemann surface is a Riemann surface, right? So there is a complete metric, Taylor metric of negative curvature. So I mean, this is it's a standard construction and Riemann geometry. So then you take the product metric of these guys, two-dimensional complex manifold, right? Then you can directly check the product metric is complete and the holomorphic section curvature is negative. Of course, the section curvature is no longer negative, but the tricky point is the holomorphic section curvature is still negative. Yeah, the holomorphic section is actually very weak. So here, the omega is our complex manifold, right? That is our complex manifold. So then we look at the map, these guys. The map F is the map of G restricted to omega. So this is our map F. So this is a local biholomorphism because you can just check, prove the determinant of F is not zero everywhere. So this must be a local biholomorphism. And then you look at the preimage of F of the point 0, 0. So you set G0, 0, G1, Z2 is 0. So you have exactly 4 points, right? You just solve these equations, you have exactly 4 points. Then also you look at the complex lines through 0, 0, right? Again, there are 2 types of these complex lines. One is omega 1, 0. The second one is omega 2 is equal K minus omega 1. You can just check this. I call the second one is the generic line. You can directly check the preimage of generic line is connected, but it's not simply connected. Yeah, it's not simply connected. So then you look at the this preimage of these guys. So you have these guys. This I call it the exception line. They are exception lines. This is the exception lines. The preimage of these exception lines, they are also it's not connected. They have two connected components. They have two connected components. However, the number of the points in F negative 1, 0, 0, that means the preimage of 0, 0 is 4, right? It means the estimate in our CM, this particular number is not true. So let's recall you what's the estimate in the CM. The estimate in the CM tells you the preimage of this point, the fiber, is less or equal to the number of the components of preimage of complex lines, right? But in that example, the number of the complex preimage of complex lines is 2, right? However, the number of the preimage at this point is 4. So this inequality is not true, right? What's the reason why it's not true? Because the preimage of a generic complex line is not simply connected. So that means the second hypothesis is not satisfied. This shows it's very important to assume the generic complex line, the preimage of such lines is simply connected. Well, if you look at this theorem, they also assume, right, the preimage of every complex line is simply connected. It's simply connected. This is very important. Okay, so yes, this is our estimate. Yes. Now we want to talk about the idea of the proof. Actually, the proof is quite similar to the proof I just mentioned, and the proof of the theorem of Nernst and Frederico Xavier, but it's much more complicated than that. It's you can think about it, it's a generalization of this argument. The theorem is a generalization of the theorem. The argument is also a generalization. Okay, so let's say the outline of the proof. So we just assume the dimension of the complex manifold. In general, they can be reduced to this case by a very complicated argument. So we argue by contradiction. So if we assume if the preimage of 0 is bigger than k, well, k is the number in the right-hand side of the theorem. Yes, k is the number of in the right-hand side of the theorem. So because the preimage of 0 is bigger than 1, right? So in particular, we can choose at least 2 different points in the preimage, right? By assumption. Well, then we fix P1 and P2. After you choose these 2 points, we fix them. When you fix them, so because this is C2, right? So we now look at the generic line. This is the generic complex line. Well, sigma is the number of exception line. Usually it's actually finite. So now because by assumption, we assume the preimage of the generic complex line is simply connected, right? So it's simply connected, then of course it's a submanifold of X, right? By assumption, X carries a Kähler matrix of negative holomorphic section curvature, right? However, the preimage of this complex line is a complex manifold. Then you look at the induced Kähler matrix, the holomorphic section curvature is also negative. This is quite interesting phenomenon for Kähler submanifold. The holomorphic section curvature is not bigger than the Abundant space. So the holomorphic section curvature is also negative. However, it's a 2-dimensional manifold. The holomorphic section curvature is the same as the section curvature. So that means for this particular 2-dimensional manifold, the Kähler matrix has non-positive, has negative section curvature. But we assume it's simply connected, right? So in particular, this is a Gardner-Adamant manifold. The expression map is a diffeomorphism. So in particular, any 2 points can be joined by a unique geodesic. So you can join a unique geodesic. You can join a unique geodesic omega L, such that omega L0 is P1, omega L1 is P2. Right? This works for any generic complex line. So now we look at the tautological line bundle of CP1. Well, this is the tautological line bundle, right? It's LV, the line is the element in the complex line. So it's a sub-bundle of CP1 times C2. Well, it's a quite standard fact in topology that the Euler number of this complex line is -1, right? It's not 0. So we, as before, we construct a section is as this. However, the section is not defined on CP1 everywhere. It's defined on CP1 minus sigma. Sigma is a finite set. Well, this is still the section. You look at the initial vector of omega L, then you look at the image of DF. Well, because P1 is not a P2, so omega L prime 0 is not a 0. And because F is a local biholomorphism, so differential F of this guy is not a 0 also. So that means S is nowhere 0 continuous section of the restriction of the L to the complement, right? So this means S is nowhere vanished. So, however, because we just assumed the preimage of the generic complex line is simply connected. We don't know the information on the other exception line, right? So that means this section is just defined on CP1 minus sigma. Well, in the theory of Neroth and Fred Xavier, they assume the preimage of every complex line is simply connected. So in that case, S is defined everywhere on CP1. So then you get a contradiction directly because you construct a nowhere vanishes section of the tautological line bundle. So, but this is impossible because the Euler number of the L is not 0. So now in our case, we cannot just get a contradiction because we don't know the information for S on this finite set, right? Then we still do something else, right? So now our strategy is the following. If you assume the preimage of 0 is bigger than K, K is actually the mean max of the number of components of the preimage of the complex lines. If you have this inequality, then we prove the local index of S of this singularity is 0. So remember, we have constructed a section, right? It's defined everywhere except these finite many points in CP1. So you can think about S as a section of L, however, with finite many singularities, right? Because it's not defined on sigma. So you can think about the singularity. So we want to prove the local index of this singularity is 0. Then, of course, you know there's a famous theorem in topology, so-called Poincare-Hopf theorem, right? By the Poincare-Hopf index theorem. You know, the order number must be 0 because the order number of this line boundary is the sum of the index of this section, right? But you know the index is 0, so the sum must be 0, so the real number must be 0. Then you get a contradiction. So the contradiction tells you must have this estimate. So then you prove the theorem. So we have to understand the index of the singularity. That's the point. Okay, so let's first remind you what's the definition of the local index. So it's actually quite standard fact in topology. You can find it in many standard textbook. So if you pick a complex line, I call it an exception line. So then you choose a neighborhood D2, right? In CP1, where D2 is diffeomorphic to open ball. Then of course the restriction of the complex line boundary to D2 is a trivial boundary, right? The associated circle boundary is also trivial. Well, then you means you choose all retention, so everything is all retention preserving. Then you look at the index. What is the index? It's the degree of the map. But you look at the boundary of this disk. The boundary of this disk, of course, is a circle, right? It's a circle. So you have a section. You have a section S. Section S, because it defined everywhere except this point, except this singularity. So S is defined over the boundary. So S is a map from the boundary to the circle bundle. The circle bundle is trivial, right? It's D2 times S1. Then you project to S1. So you get this map. Here's this map. So the map is from circle to circle, right? It's a map from circle to circle. Of course, you can look at degree. of this map, right? The degree of this map is the local index section. Okay, that's the definition. Okay, so this actually works for any section, right? In particular, it works for our section as constructed before, right? How constructed this section is. So you define a map, right? Now the point is, you define a map, this guy, the degree of this guy is equal to the local index of the section S. So now we want to construct another section, okay? So because we assume the number of the parameter of 0 is bigger than k. K is the number of the, is the maximum number of the connecting components of parameter of compass line. Okay, in particular, the parameter of the exception line has at most k connected components, right? That means there must exist some component of this guy that contains at least 2 different points, P3, P4, inside this guy, right? So this is a simple counting argument, right? Because the number of this guy is bigger than k, while the number of this guy has at the most k connected component. So there must exist at least 2 points, P3, P4, lies in the same component, right? Yes. So P3, P4 is another 2 points. It could be the same as P1, P2. Remember, we by our previous argument, we already choose 2 different points in the parameter of 0, right? P1, P2. Now we have constructed another 2 points, P3 and P4. They are not necessarily pairwise distributed, but you have P1 is not P2, P3 is not P4. Okay, so of course, P1, P2, they are fixed for any complex line. They are fixed. But P3, P4, that depends on the choice of the exception lines. Then we can still prove by continuity argument, we can still prove inside this guy, there's also unique geodesic joining P3 and P4. Okay, so now we want to construct another section, this section. This section is again from a map from circle to circle. So this guy is this construct as this. So what is sigma? Sigma is the following. As I just mentioned, right? By assumption, for any L inside this D2, right? If L is not the exception line, the parameter of L is one connected. So that means there's a unique geodesic VL such that VL0 is P3, VL1 is P4. So then you look at the initial vector and look at the image of the guys, but everything is constructed as before, right? But however, we construct using the point P3 and P4. Okay, so this is a next section, construct using P3 and P4, and then map is constructed using this section. So why this is useful? Because you observe that actually sigma is defined over, there is a continuous extension of sigma to D2, right? It's no longer just defined, the boundary can be defined on the whole disk. Well, remember for the section we have constructed before S, it's defined everywhere except the singularity, right? Now, for this construct here, sigma can be defined everywhere on the disk. It can also be defined on the singularity, because by assumption, the singularity L alpha, there is also a unique geodesic join P3 and P4. That means this map it can be extended to a map from D2 to circle. So we have constructed 2 different sections and 2 different maps. Using P1 and P2, we construct a map phi, and we using P3 and P4, we construct a map cassette. So the most difficult part we've tried to prove is actually we have proved these 2 maps, they are homotopy. Well, this is the most technical issue in the proof. We proved that these two maps, they are homotopy. So in particular, the degree is the same, right? They are both maps from circle to circle, and they are homotopy. So the degree must be same, right? The degree must be same. However, for Coset, this map, there is a continuous extension to disk to circle. Well, then it's elementary to prove the degree of the second map actually is 0. This means the degree of phi is also 0. Well, as I explained before, the degree of this map is the local index of the section, right? So that means the local index of the section is also 0. Then you take the sum over all the complex lines, then apply the Pocket-Hopf index theorem. We know the Euler number of the line bundle is 0. But this is impossible because by construction, we know the Euler number is -1. So then we get a contradiction. Well, the most difficult point is you try to prove this is homotopic. Then you tools from Riemannian geometry. So let's say let's say something about this proof again. So the basic idea is try to apply Riemannian geometry and topological arguments to study the global injectivity. Of course, you put conditions. The conditions are topological and geometric. Then you prove it's injective. So you want to find the philosophy behind this. Right? Of course, this is quite different from the famous the Jacobi conjecture. The Jacobi conjecture is algebraic conditions, right? It's polynomial local biholomorphism, and you want to prove it's global injective. Of course, it's hard to relate the algebraic condition to geometric and topological conditions. I think Fred, Harry, and Leonard, they also have conjectures tells you if you have a local diffeomorphism between Rn, if the preimage of the hyperplane is connected, then it's injective. They managed to show if this conjecture is true, then Jacobi conjecture is true. Unfortunately, I think in the talk later in this section, I don't remember who actually there's a talk. They will show the Fred conjecture is not true. They have found a counterexample. So that means, right, if you want to apply geometric topology, this kind of stuff to understand the Jacobi conjecture, but it's still hard. So of course, we look at different directions, right? We find some different conditions, it's geometric condition and topological conditions, and try to apply tools from geometry and topology. Then you prove it global injective. This is the idea in the proof, and yes. I think I stop here. Thank you.
So let's thank the speaker.
Oh, thank you.
Okay, thank you very much, Chen. So thank you. So thank you very much. Your very nice talk, and I think that we don't have time for questions now because at 12 o'clock and 50 will be the second talk. So we can discuss with the speaker later on.
Okay. Yes.
So we will come back to our second talk at in 2 minutes at 12.
Okay.
Okay. Thank you.
Okay. Thank you. Let's just stop. Finish the talk and then quit. Okay.
Yes. Let's thank our speaker again.
Okay. Thank you.